Alright, so today we are going to continue our discussion of properties of logarithms, abbreviated logs a lot of times, so that is confusing you. Logs, logarithms, they're the same. And we're going to be talking about the change of base formula, but let's start here by me asking you, what if I asked you to evaluate this log, which is log base 2 of 70 is how I would read that. Um, so you can think about it, like what are your skills you've learned? Well, can I take 70 and rewrite it with that power of 2, like 2 to some power, right? The answer is no. It's pretty obvious, right? 2 to some power is never going to be 70. Um, it will be, but it's really ugly, right? And you're not going to be able to think about that off the top of your head. So we need something else, right? We need to be able to calculate it in a different way. Most calculators only evaluate logs with base 10, and we've seen that's really just shown as log a lot of time on the calculator, or base E, which is your natural log, abbreviated as ln. This first calculator is what you see on Canvas. You can see your natural log here, and you can see your log base 10 there, which again, over here on this calculator, you have your natural log and your just log log, which doesn't have a 10 there, but remember they're the same. So most calculators just have these two abbreviations for those types of bases. Technically, you can do more complicated ones over here on the graphing calculator, but for now, I'm going to show you why we can use just those regular bases, 10 and E. We currently have log base 2, right, for this question I asked you at the start of this lesson. But we can actually change that base, but we have to do something about it, right? And this whole property is called the change of base property. So let's say I was giving you a log like this, right? Kind of similar to what we have here. In this case, 2 is the same as B and 70 is the same as A. So what happened here on this right-hand side, had we take that left side log and change it into this quotient here? Well, it looks like what you were taking the log over here became what you're taking the log in the numerator, and the base became what you're taking the log of in the denominator. What's interesting that is not on the left-hand side is this x here. So what is x? Well, as you can see, it's in the base position of a log. And that x that we put in there can literally be any possible base. So this could be log base 11 of A over log base 11 of B, right? This could be log base 50 of A over log base 50 of B. And this could go on and on and on. As long as that base is the same in the numerator and denominator, and it has to be positive and it cannot be 1, but it can literally be anything. Now, why would this be helpful to us? Well, we probably want to not use log base 11s and log base 50s because we're going to run into probably a similar situation here as we did in the beginning a lot of times. So what are bases that would be helpful for us to use are things like common logs or natural logs, right? Because we can actually evaluate those in our calculator. We will have to round, but it'll be okay. So I'm trying to prove a point on these next examples. I still want you to evaluate this, right? But I want you to use the change of base. You can kind of see that fraction, quotient, change, and all of these just using different bases that I outlined there in red. So using base 10, common logs, base E, and then base 8. And I'll talk about base 8 here in a second. So looking at log base 2 of 70, we rewrote that as log of 70 over log of 2. And you can see that I didn't write the base 10, but that's okay. Even though they're not written, we assume it's base 10. So that's acceptable to us. And then it's pretty easy for us to use that in our calculator. So like you'd use this button for both of them. I'll just write out here what it would generally look like. So it'd be like log of 70 divided by log of 2. And if you do that, I've already done this for you, you get a rounded answer. And a lot of these are going to be rounded. That's why you have those little curlies there. you get about 6.13, and I'll tell you how to round. Sorry, guys, not sure what that is. To like the tens or hundreds or something like that. So let's say I tell you to use base e. Well, that's the same as using natural logs, right? So kind of implied in both of these things. I would use this button here, natural log of 70 over natural log of 2. I'd go ahead and do that on your calculator if you can with me. Guess what you get? Shocker, 6.13. The same exact answer that you got if you used base 10. Now, base 8 kind of defeats our purpose here because, right, looking at this calculator, do you see anywhere you can use base 8? Not really. There is a special way you can do it over here, but for the sake of this activity, I want you to mainly be looking at log base 10 and natural logs because of this reason of it's easier for us to calculate. But guess what your answer will be if you use log base 8? It'll be 6.13 about. So what if I used log base 50? Guess what? It'd be 6.13. What if I used log base 7, right? It'd be 6.13. You're going to get the same answer no matter what the base is if you use this change of base properly. So let's do some examples. Evaluate each log found round to the nearest hundredth. That's 2 decimal places when necessary. Okay, so the first thing you always want to do is to see if you actually need a calculator on this. So, can I write this as 3 to some power here, right? Can I take 20 and rewrite it as 3 to some power? It's pretty obvious that 20 is not a power of 3, so that's not going to work for us. So let's use change of base. So what bases could I use? Well, the easiest ones would be base 10. So that's what this one would look like with base 10, right? The 20 comes up top, the base becomes what you're taking the log of down there, or you could do natural logs. Natural log of 20 over natural log of 3, right? Or you could literally use any other base, but again, why would you do that, right? If we have perfectly good options here. And guess what happens when you put both of those in? It does not matter, you'll get the same answer. And the answer for this is about 2.73. So you'd want to leave that as your answer, okay? This next one, can I evaluate it without a calculator? Can I write 100 as a power of 7? The answer is no, right? Can't do that. So now let's use change of base. Well, we could just do log of 100 over log of 7, or we could do natural log of 100 over natural log of 7, or some other base that's not really helpful for us in this case, right? Either way, you'll get this answer, which is 2.37. And it's going to have to be a rounded answer. It's not going to be pretty, which you can see why it's not going to be pretty here, right? Because 7 to a power is never going to give you that number. Same thing here. 0.3 is the same as 3/10. Am I going to be able to write 4 to some power to give me that? The answer is no, so we use change of base. Let's say I used common logs. It would look like this if I use natural logs, right? Or if I used some other property, log, not other property, other base, right? Doesn't matter. Either way, you're going to get, what do you get for this one? Negative 0.87. And I would be stopping this video and like double checking that you get those in your calculator, just as a helpful hint. So what do we have here? Why is this different than the last ones? Well, do you see 2 logs, right? It kind of looks like if you're thinking about your formula we learned at the beginning, log base b of a equals log of a, oops, over log of b, right? That's the change of base formula. So it looks kind of the opposite direction, whereas the other problems we've been using start with 1 log and go to 2. You guys see these are technically both base 10 here. So it looks like they used the change of base property, but let's see if we can go back the other way to 1 log and see why that would work. And you may be already noticing some similarities between 81 and 3 from what we learned last week. So what would that mean? Well, it looks like they use base 10, right? But how do you take that back to a log? Well, the numerator is what you end up taking the log of, right? And the b here, whatever is in your denominator, becomes your base. So that's the same as log base 3 of 81, right? Now, why is this helpful? Okay, well, in all these past examples, I've asked you, right, can I write 100 as a power of that base? Can I write 3 as a power of 20? Sorry, can I write 20 as a power of 3, right? I've asked you that. What is special about this one? Well, 81 can be written as a base of 3. And what would that be? Log base 3 of 3 to the 4th is 81. So we've seen how this just ends up being our answer here. So our answer is 4. And remember, another way of thinking of that is doing the log base 3 of 81 equals x. It's supposed to be an L, sorry. And you can say 3 to what power is 81, right? And clearly that's 4. But this is our answer here. It turns out being pretty nice because we're doing the reverse process of the change of base. Last couple problems are more just like a simplification. So what if I gave you this multiplication problem off to the right and I asked you to simplify it? Well, log base 6 is a base of 10, right? And this has a base of 6. So could I rewrite this second one with the base of 10? Well, I can because, you know, you have this property of change of base. So what would that be? Log of a over log of 6. Then look what happens. Just with multiplication, numerator and denominator cancel out. I'm just left with what's up here. So log of a, which goes with that one there. Okay, so you're just kind of simplifying using your change of base where necessary. Last one. I want to make this left-hand side look like this right-hand side. So let me start by writing down what I started with. Log base 8 of 1,000. So let's start by using change of base. And what base would I change it to? Well, if I want to show these are equivalent, I'd probably change it to base 2, right? So log, you put your 1,000 on the top. Log, you put your 8 on the bottom. And I want to use the same base here, and I want to use base 2. Well, why is that helpful? If you notice, your bottom here can simplify because 8 can be written as a power of that 2 base, right? So what can it be written as? Well, your numerator is not changing right now, but this goes to log base 2 of 2 to the 3rd. So what does this denominator simplify to? Kind of simplifies to log base 2 of 1,000 over 3. Now this might seem a little weird to think about, but that's the same as 1/3 times log base 2 of 1,000, right? Dividing by 3, that's a positive 3 by the way, is the same as multiplying by 1/3, right? And you can use the power property that we've learned, right? That just becomes the power of what you're taking the log of. So this becomes log base 2 of 1,000 to the 1/3. And you can simplify. Taking something to the 1/3, we've kind of worked on this before, is the same as taking that cube root of that number. And so basically what times what times what gives me 1,000. This is pretty easy with zeros. This becomes log base 2 of 10. And as you notice, that's what I wanted to show it was equal to. These last two problems are a little more challenging, and look back on these to help you with your homework.